Welcome to Chapter 1 of Master Books Physics: Physics, Wisdom, and Science. So you should have already read Chapter 1. If you have not read it yet, then nothing in this video will make any sense. Stop watching and immediately go and read the chapter if you have not. If you have, good job. You can follow directions. Keep reading, keep watching, and read through your notes as you proceed. If you have any questions, bring them to class or message your instructor. Now we know that natural laws worked from the very beginning of creation of the world. Physics is just a study of those natural laws. Now, according to the Bible, light was created before the sun, which makes sense in a way. Natural law is a description of observation. Natural laws were created and are maintained by God. Now, I want to point out that when someone is studying science or someone is trusting the science, they're not necessarily being heretical. And that's something that the church had a problem with a while back. Science, in its purest form, is just seeking to understand the world around us. It's observing what God has made and trying to appreciate His creation through understanding it. At its very basic core, it is an appreciation of God's creation. Now, a long time ago, there was this really smart guy named Aristotle, and he observed all kinds of things about the world. Problem was, Aristotle did not test his ideas with measurements and experiments. Now, part of that is because he really didn't have the technology to do so. I mean, he didn't have a watch. All he had was like a sundial. So it was really hard to time things. All he really had was like his pulse. And I don't know if he thought to do that. Now, Aristotle concluded that heavier objects fall faster than lighter objects. We know now that that is not true, that gravity acts on all objects the same way. He also taught that a thrown ball kept moving after leaving a person's hand because air pushed it. He didn't know anything about momentum and inertia. We know now that a feather will fall slower than a rock, not because of its weight, but because of air resistance. Think about it like this. If you have a 2-pound rock and a 200-pound man in a parachute and both jump out of an airplane, which one's going to hit the ground first? The 2-pound rock, because there's less air resistance. The parachute is providing air resistance and drag for the guy, the 200-pound guy, but the 200-pound guy weighs more than the 2-pound rock. So air resistance plays a big role in how fast something falls. So that's something to think about. Now, another smart guy was Galileo, and he used lenses to make a refracting telescope so that he could examine the heavens. He discovered craters on the moon, four moons around Jupiter, sunspots, phases of Venus, and he was a smart enough guy to realize that for Venus to have phases, it meant that it went around the sun, not the sun around Venus. And those observations did not sit well with the church. That's completely against what they taught. So he was declared a heretic and placed under house arrest. See, back then they believed that the sun went around the earth, and that was the way that God created it, that the world was the center. And, that's what happens when you have people who um, don't really know science. They kind of eschew science because, they think they're right. It didn't have anything to do with the fact that they were Christian or that they were supporting the Bible. Their beliefs were strictly based on the fact that they were trying to control the narrative. Copernicus and Galileo said that the planets revolved around the sun and not the sun around the earth. These were both really smart guys that made their own separate observations and came to the same conclusions. Science begins with observations, forming the hypothesis and using experiments to test the hypothesis, not the other way around. This is called the scientific method. We use experimentation to test ideas rather than just accept what seems reasonable, which honestly, in Aristotle's defense, that's all he could do because, like I said, he didn't have the technology to really do the experiments. Now, the scientific method involves observing something in the real world and having a question about it. Then you do a little bit of research to figure out, can you answer that question? Or how can you answer that question? Once we think we have the answer, that's the hypothesis, by the way. That's your what you think the answer or the solution is. Then we have to test it to make sure we're right. That's the experiment. Then we look at the results of the experiment, and if the results of the experiment do not jive with our hypothesis, then we have to change the hypothesis. We have to go back to the observation and say, what did I miss? What am I not seeing? How can I change the hypothesis? We never, ever change the results of the hypothesis. That is called, or the results of the experiment. That's called falsifying data. We cannot falsify our data. Instead, we change our guess, we change our hypothesis, and then repeat the experiment until we can create a solid, repeatable conclusion with the same result every single time. A well supported hypothesis is called a theory. And in order for it to be a theory, those experiments that we create to explain our hypothesis must be repeatable. Hypotheses and theories, they're always being replaced as new insights are gained. Not only new insights, but as new technology is developed that helps us make better experiments, then sometimes we find out we're wrong. Like, for instance, back when Aristotle, all he had for measurement purposes was a sundial, well, he couldn't measure stuff in time very well, could he? But now we have stopwatches and micrometers and things like that where we are able to measure things in time very, very accurately. So, in science, there are no absolutes. There's only what we understand right now. And as new technologies develop that help us understand things a little bit better, those hypotheses and theories, they get replaced. On to the math bit. If you haven't dealt with the metric system yet, it's what the rest of the world uses for measurement. We're kind of, the US is stuck in the English system. It's okay. Maybe, when I was a kid, which was about, 35 something or more years ago. Yeah, I'm old. Um, they told us that by the time you're an adult, the entire world is going to be using the metric system. Well, guess what? The US is still not using the metric system. Not really. Here and there, but not really. Once you understand it, though, it's a lot easier to use mathematically. If you look at the chart here, every place value is just a shift to the right or the left of the decimal, and that's why it's so much easier to use mathematically. You just move the decimal point to convert from one unit to the other. Now, the missing label on the previous chart is going to be the unit. If it's length, it's going to be a meter. If it is volume, it's going to be a liter. And if it's mass or weight, it's going to be a gram. The prefix is then paired with the unit to show the size of the unit of measure. So a centimeter is going to be 0.01 of a meter, and a kilogram is 1,000 grams. A deciliter is going to be 0.1 of liter because, 0.1 is the place value of deci. And then when you put that with a liter, that's what it is as its value. Now, for instance, meter, that's our unit of measure of length in the metric system. 1 meter has or is equal to 0.001 kilometers because it takes 1,000 meters to make 1 kilometer. The same is true for a hectometer. It takes 100 meters to make a hectometer. So 1 meter is 0.01 of a hectometer. You can see the different values here. And let's go look at centimeters, for instance. That's next to the last on the list. There's 100 centimeters in 1 meter because of the place value of the centimeter. Conversion in the metric system, as we've seen, is super easy. Now, the way you do it mathematically is you just take the original value, divided by the place value to convert it to a different unit. Or we should say the unit value instead of the original value. So if I wanted to take 2 meters and convert it to centimeters, I would take that 2 divided by 0.01, and that gives me 200 centimeters. If I have 2 meters and I want to convert it into kilometers, see, what part of a kilometer is 2 meters, I would divide it by 1,000. And then that would give me 0.002 kilometers. That's how much 2 meters is in relationship to a kilometer. So you could see finding um, the different units of measure for something is really easy to convert. You just move that decimal place. Conversion from metric to English or vice versa. It's a little bit harder. You got to have some kind of a crossover reference. For us, in regards to length, we use inches versus centimeters. We know that 1 inch is equal to 2.54 centimeters. With that reference, we can convert 200 centimeters into inches. So 200 divided by 2.54 would be 78.74 inches. But how do you know which number to use where? Well, if we use the fraction form, it allows us to see the whole reference, so we know that we've got things in the right spot. And the way we know that things are in the right spot is whatever the original unit of measure is, which in this case is centimeters, that is what goes in the denominator of the next fraction. And that allows us to cancel out that unit of measure and convert it into the other one, which in this case is inches. So we would have 200 times 1, so that'd be 200 divided by 2.54, which is in the denominator, which gives us the 78.74 inches. It's a little bit easier to see it this way. So that's the way that we are going to use it in physics, which is the same way that we learned in pre-algebra, algebra 1, algebra 2, etc., and so on. We can even convert larger problems, which you've probably already done if you've had algebra 2. Here we're doing 20 meters into yards. And if you notice, we go from meters to centimeters, centimeters to inches, inches to feet, feet to yards. And then we multiply straight across the top and straight across the bottom to create a fraction. And then that fraction is the division problem that we use to find that 20 meters is 21.87 yards. Now here's a little bit better illustration of how everything cancels out. We treat our unit of measures just like a variable, and a variable is just a factor. So we're basically canceling factors, which are the unit of measure, in each of the calculations. So when we duplicate meter in the numerator, the first fraction, and the denominator, the second, we can eliminate it. Same thing for centimeters, inches, and feet. So your unit of measure for your solution is always going to be the unit of measure that is in the numerator of the final fraction. And you're just going to transfer that to the end, to the solution, so that when you do that division problem, that is the unit of measure that you end up with. Volume is something that we learned how to do in all of the algebras as well. We know that we can find that by multiplying length by width by height, or whatever 3 units we have. And they're all lengths. They're all a length of some kind, a distance of some kind. We just give them 3 different names so we can keep track of what they are, separate them. The basic unit of mass in the metric system is going to be grams. In the English system, we use ounces, but we are going to be using the metric system in physics, so it's important to understand what the metric system units of measure are. And when we talk about time in the metric system, that unit of measure is seconds. Now, density is something else we're going to be talking about. Density is defined as mass divided by volume. That's why it's important to know how to calculate volume. For a boat to float on water, it has to have a density below water. For anything to be carried by anything else, it has to be, it has to be lighter than what is carrying it. Think about this. If you pick up a box, the box has to be lighter than you are, or you can't pick it up. I mean, that's just common sense, right? You can't pick up something that is heavier than you are. So picture water as carrying a boat. So it makes sense in that illustration that the boat has to be lighter than the water. Now, in small quantities, that's not true. We know that the water would be lighter than the boat if we had the equal amount of water, the volume, in regards to the boat. But density doesn't work that way. It is all about the mass, the total mass of the water. And when you think about a lake or a river, you couldn't float a boat the size of the Titanic in a kiddie pool. It wouldn't work, right? But in relationship, the size of the ocean, the amount of water that's in the ocean in relationship to the size of the Titanic or the size of a boat of any size, the water is going to have a higher density. There's more of it. And the boat is going to have a smaller density. There's less of it. And that makes it basically lighter than the water. So, density has to be lighter for it to float. That's what you need to remember. The density of something, excuse me, has to be lighter for it to be carried by the other thing. And that's all we have for this video for chapter 1. There's going to be some questions following this video. Take your time. Do a good job. There's going to be some fill in the blank and some math problems. Write down the questions on the screen as they come up in the GenoPod. Make sure you write them down in your notes with the correct answers. And if you don't know what the correct answer is, you can't get the correct answer, go back through the video. Most of the answers are in the video. Now, the math problems, you are going to have the formulas given to you in the video. So if you forgot how to do it, go back and look at the video. Find the formula. Do the problem. Write down the correct answer. Most importantly, ask for help when you need it. If there's something that doesn't make sense, bring those questions to class. If you have a problem that you just can't solve, message your instructor. Smart people ask for help when they need it. Be smart.